Hello, everyone. Today, we are going to discuss Semester 5 Mechanical Engineering Heat Transfer.
Chattering.
Thank you, Professor Ananya. This subject is the backbone of mechanical engineering and helps students connect theory with real-world mechanical industry.
Hello, everyone, and welcome. Today, we're jumping right into one of the most important subjects in mechanical engineering, heat transfer. It's this, invisible force that's behind so many things in our world.
I mean, think about it for a second. It happens to all of us, right? You've got a nice hot cup of chai, and before you know it, it's cold. But then you play a game on your phone for a while, and suddenly it's hot enough to warm your hands. What's going on there?
Well, the answer to both those things is exactly the same. Heat is on a journey. It's always moving from a hotter place to a cooler place. So for this explainer, we're going to become heat trackers and follow its path.
So, if heat is a traveler, how does it get around? Does it take a bus, a train? Well, kinda. It actually has three main roads it can take to get from point A to point B. First up, we have conduction. This is basically heat transfer by direct touch. It's just like in college when you're all sitting on a long bench and passing tiffin boxes down the line. Each person passes it to the next without leaving their spot. That's exactly how conduction works. It's heat moving through something stationary, like a metal spoon in your hot chai. Now, if we zoom in, way in, to the atomic level, what's actually happening? Well, inside solids, it's one of two things. Either the atoms themselves are vibrating and bumping into their neighbors, passing the energy along, or, in metals, you have these tiny free electrons that just run around carrying the heat. Simple as that. All right, path number 2 is convection. Now, this is all about movement. The heat actually hitches a ride on a moving fluid. And by fluid, I mean a liquid or a gas. The best example is the steam coming out of a pressure cooker at home. That hot steam is physically moving and carrying all that heat energy with it. That's convection in action. And finally, the third path is radiation. This one is pretty cool because it doesn't need to touch anything. It doesn't need a medium to travel. It's just pure energy moving in waves. Think about standing near a tandoor. You feel that intense heat even if you're not touching it, right? That warmth traveling through the air to you, that's radiation. Okay, so out of those three paths, conduction is a really big deal in engineering. It's everywhere. So naturally, it has its own rulebook, a fundamental law that tells us exactly how it behaves. And here it is, Fourier's law. Yeah, I know, it looks a bit mathematical, but trust me, the idea behind it is super simple. It's basically the rule of the road for heat. It tells us how fast heat is going to travel through something. And hey, to make sure you never forget the key parts, here's a little trick. Just remember, heat flow, or Q, depends on the material's K character, the area it can flow through, and the temperature push that's making it move. Easy, right? So, quick check-in. What's that fundamental law called that acts as the rule book for heat conduction?
Now this is where things get really interesting. We know the rule, but what happens when the path changes shape? Because you see, heat flowing through a flat wall is very different from heat flowing through a round pipe. So on the left, you see a flat wall, right? Super straightforward. Heat just moves in a straight line from the hot side to the cold side. The area is constant. But now look at the pipe on the right. Here, the heat is spreading out, radially. As it moves from the inside to the outside, the area it's passing through keeps getting bigger and bigger. That changes everything, and it means we have to adjust our formula. And you can probably guess what happens with a sphere, right? It's the same idea, but even more so. The heat spreads out in every direction, so that area term in our formula changes again. So let me ask you this. What's the one key thing in that conduction equation that has to change when we go from a flat wall to a pipe or a sphere? Okay, so we've been watching how heat travels, but we're engineers. We don't just watch, we control things. So how can we use all this to our advantage and actually make heat move faster when we need it to? And we need to do this all the time. Think about the processor in your computer or the engine of a motorcycle. These things get crazy hot. And if we don't get that heat away from them, and fast, they will literally fry themselves. So what's the brilliant solution? Fins. Yeah, those ridges you see on engines and all sorts of electronics. They are basically super highways for heat, giving it a much bigger road to escape from. And how they work is a perfect two-step process. First, heat conducts from the hot surface right into the base of the fin.
Then, for step 2, the fin's huge surface area dumps all that heat into the surrounding air using convection. See? It's a perfect team-up of conduction and convection.
And of course, we need to be able to calculate all this. This formula lets us figure out exactly how much heat a fin can get rid of. This is how we can design the perfect cooling system for anything, from a tiny chip to a massive engine.
Okay, just to lock this in, what is the number one reason, the primary purpose, for adding all those fins to a hot surface?
All right, we've covered a lot, but let's talk about the big picture. All this theory is great for your exams, but why does it really matter for your future?
Look, this is not just textbook stuff. This is what's building our future. We're talking about keeping the massive batteries in electric vehicles cool so they don't catch fire. It's about designing CPUs that are faster than anything we've seen before. It's how we build systems for spacecraft and how we make green energy solutions actually work.
So I want you to remember this. When you master the flow of heat, you're not just passing a subject. You're learning how to control energy itself. And that's a superpower. It allows you to make things faster, safer, and more efficient. So mastering this flow, it really is about learning how to build the future.